All right. I'm going to open up the geometry here. This video actually has audio. We have your wind tunnel with the sketch of the flat plate, which should be, from the dimensions, it's H36, which is 23 centimeters in length by 0.2 centimeters in height, or 2 millimeters. This is just measuring from the center line of the wind tunnel. All the wind tunnel dimensions is the same as from previous labs. You can go on to the meshing. Go to the mesh here, can edit. I'm gonna close out Discord real quick here. Okay, got our mesh here. For the mesh, we did triangles method with edge sizing. Made the mesh to be 2 to the negative 3 meters. Edge sizing should be, I don't know what's happening with my mouse right now. Around all 4 edges. We have inflation here, which is from here. Body sizing. We have name selections, where I named the top plate, specifically top plate, bottom plate, as the actual bottom plate. And we have sides. This is what the mesh looks like. As you can see, we have the inflation coming over here and the edge sizing. So you have a lot more mesh closer to the flat plate. Thing looks pretty good there. For the purpose of the video, I'm not going to remesh it because this took like 15 to 20 minutes to actually mesh. So I'm just gonna speed through this video. You enter the setup into the solution. Sorry about the Discord. Let me quit here. There. All right. So we have our wind tunnel here. We're gonna go to models. We have the turn energy on with viscous K epsilon standard model with enhanced wall treatment, turned on pressure gradient effects and thermal effects. If you look here, the boundary conditions in the inlet, we used the contraction ratio to accurately get the same free stream velocity in the testing chamber as we did in the lab. So 2.319 is our velocity magnitude for 45 hertz to get a velocity of 8.95. meters per second in the wind tunnel. We also need to go to reference values and change velocity here to 8.95. This is your free stream reference velocity. Since ANSYS doesn't know your free stream because there's different velocities in entrance and the wind tunnel itself. I need to pull up the other one. Yes. Here. We're doing on time on the video, 6 minutes. Okay. Same thing here in the small energy on viscous. Okay, epsilon with the hand-small treatment. Plus your inlet's the same. Your reference values should all be air. You see the velocity is 8.95. Air is going to be 1 since it's 2D. 1.4 for specific heat ratio. And if you run it, run the calculation, Alright, calculation's done. Now take a look at the contours, velocity contours. That's what they look like. We're going to pull this up actually later in a different software, but just get a good idea of what it looks like. Have that. I can zoom in here. And I crashed. Probably. I'm gonna have to reload it. Read it again. We got the XY plot. So we got this is gonna be the skin friction coefficient plot. We can either take a bunch of lines and do it this way. You get something like this, or we do it this way where we have just the top plate wall that we labeled earlier. I'm gonna change this to skin friction coefficient real quick just for purposes of showing. Plot, and then we'll plot, and this is fairly close to like 0, which is as seen in the actual. If we go here to our shear stress as well, you can see the plot there. It's essentially the same. It's got the derivative of it, so that's right. And then the velocity, we want this to be 1 and this to be 0 because we want the axis to be changed around. We want the position on the x or the y-axis. We're going to be going to velocity once more, and then we're going to be looking at 0.2. So comparing from the lab, that's what it looks like. So we have the boundary layer around at like 2 millimeters or so at 0.2 centimeters, 2 millimeters at 2 millimeters. If we go to 8 centimeters, when we look at it, you can see the boundary layer is developed. You get 0.99, and you get infinity further up. That'll be calculated later and not in the video, but just to show. And if you go to 16, so you plot, you see it's also just fully developed, but just for fun, so we can plot and see them all in the same graph if you want. And as you can see, they all kind of converge right here. So it's kind of where the boundary layer starts lying. And the boundary layer kind of doesn't get as big further right later, from 0.2 centimeters, 8 centimeters, 60 centimeters. I already showed that. I'm gonna go show the contours. Okay, the contours are down here, but in order to do that, you need to go here for contours. You press contours, and then if I go to also contour, that's what the menu opens up. Symmetry 1 is usually what you want to choose for the locations. Then you're going to choose velocity, press apply. Put 25 contours for this. You can put as many as you want. 25 just looks good. Let's recenter this and just get zoomed in on the flat plate. Even further in, actually. Let me get to the front. If I turn off the contour and we just want to take a look at the streamlines, so you get streamlines or the velocity vectors. You click this button right here. It says vectors. Take you to this kind of menu right here. Again, symmetry 1. You want all these settings basically. Factor of 1 and all domains. I put the symbol size to 0.01, so you can see it. As you see, there's more vectors around the flat plate because of the different mesh stuff that we put on, like the edge sizing and the inflation. We get a better idea of what the boundary layer looks like on the flat plate. You can kind of see it here. Ooh, I tilted it. But yeah, if I go further here, you can see the boundary layer even better. As it starts to develop, you can see the zero skin friction coefficient, or zero shear stress. Yeah, that's basically it.